Good afternoon, everybody. Welcome to this colloquium theory term. Our speaker today, Sir Chris Llewellyn-Smith, a very eminent scientist, and importantly, a predecessor of mine as chairman of department. We don't call it chairman any longer, but Sir Chris actually was head of department in a very important time for physics between 1987 and 1992, when the 6 sub-departments were essentially coalesced into a single physics department. And I think Chris was the spearhead behind this amalgamation of departments. And he has a very long and distinguished career, which you'll have to bear with me. He did his bachelor's degree here in physics and a DPhil in theoretical particle physics here in Oxford. He did postdocs at CERN and SLAC, so Stanford Linear Collider. He then went to CERN as a staff member before moving back to Oxford as a faculty position and college fellowship at St. John's. After that, he went on secondment and became the director of CERN for 5 years, I think. And shortly after that, became the director of left CERN and became the director of the Culham project near to here, the Plasma Fusion Laboratory in Culham. And another very interesting project that Chris had was during starting in 2008, he was director of a synchrotron radiation facility in the Middle East, which was a collaboration between, I think, quite a few Middle Eastern countries, including Israel and the Palestine Authority. So an example of how science can say, and Iran. Okay, so an interesting example of how science can bring warring nations together. So Chris is a fellow of the Royal Society, has a host of other prizes, which I won't go through. And what's relevant today is that he led a large-scale study, government study into electricity storage, which I think reported about 2 years ago. And so I'm guessing that you are going to tell us about some of the results and findings of that report. Please welcome Sir Chris Llewellyn-Smith.
Thank you very much, Andrew. I was talking to some of you before about the colloquium. When I was a student, my supervisor was Dick Darlitz, but the head of department was Rudy Piles. And Piles had all the new students in, and he said to us, I'm not actually your supervisor, but I regard myself as supervisor of all the students. When you leave, I will be asked to write a letter of recommendation about you. I'd like to write that you have a broad knowledge of physics. If I see you in the colloquium every week, I will write that. And if I don't, I won't. But the trouble is now, people are all very busy and they can watch online and so on. I am going to talk about the highlights of the Royal Society's study of large-scale electricity storage, and then more recent work that builds on that, extends and further quantifies it. This is a bit tricky because I think there are 3 audiences. There are some people, maybe some online, I know there's 25 people online or something, who've heard me talk about this and even were part of the report many times, and they will only be interested in the new work. Then there are other people who have a very good knowledge of energy, but they maybe haven't heard me talk about electricity storage. I've spoken about it many times in Oxford and around the world and around the country, but not in the physics department. And then there's finally people who are very interested in energy, but they haven't worked in it, so they don't necessarily know all the jargon. So I'm going to address myself to the 3rd category of people. Now, our report, the Royal Society report, was published in September 2023. If I have my time again, by the way, it's an 85-page report, and there's a 201-page supplementary information. Here is the report. What was I going to say? There's been no serious criticism, I would have said. But if I have my time again, I would write it differently because it's become quite clear that some things were not understood. and I will point those out. And the other thing that's changed is that there have been cost assumptions that we made were very out of date, because there have been big increases in commodity prices, the cost of offshore wind, and so on. And due to bottlenecks and increases in commodity prices, but it's important to realize that those affect all forms of electricity supply, ways of meeting electricity demand. Now, this talk is about Great Britain, and for those of you who are not energy freaks, you may not know that Northern Ireland's electricity grid and market are integrated with those of the Republic of Ireland. They're completely separate from Great Britain. Now, our methodology can be used anywhere. I mean, when we decide, say, this is how efficient electrolyzers will be, that doesn't depend on geography. But supply and the role of storage depend on geography and geology. If we're talking about North Africa, we'd have much more solar. If we're talking about Japan, we wouldn't be able to, there are no large salt deposits, so we wouldn't be able to consider storing hydrogen at scale in underground salt caverns. But what is clear as of all projections of the future, that as fossil fuels are phased out, an increasing percentage of the need for energy will be met by electricity, as phased out of transport, industrial heating, and so on. And an increasing percentage of electricity will be met by solar and wind. In fact, our government's predictions are that by 2030, the supply of wind and solar in the proportions that we assume will be something like 25% bigger than the demand for electricity. Now, we're going to assume that in Great Britain in 2050, supply from solar and wind will be mixed 20% solar, 80% wind, and then with a certain onshore, offshore wind, which is not so critical. This minimizes the amount that has to be curtailed, just thrown away, with headlines in the Daily Mail, Britain pays so much a year for electricity that's never used or stored. Now, the key thing that we have stressed is the variability of wind, which may seem rather obvious. The wind does not always blow, the sun does not always shine. Wind and solar must be therefore complemented by large-scale flexible supply and or storing the excess when they produce more than needed at that moment to meet demand and using it later. But the only large-scale low-carbon sources are nuclear, bioenergy with carbon capture and storage, and gas with CCS, and hydro in some places in the world, but not in the UK. But they're expensive, especially if operated flexibly. Large capital costs, and you want to run them flat out. So it looks a priori as if storage will be important, and that's what we find. The CCS is limited by emissions of fugitive CO2 and upstream methane leakage. Now, the upstream methane leakage, I see Miles Allen is here, so he and I have written a note about this, has been grossly underestimated. For some reason, the International Panel on Climate Change compared the effect of a pulse of methane. You put 1 ton of methane or 1 pound of carbon dioxide into the atmosphere. What's the effect after 100 years? Who cares? We're all dead after 100 years. The real question is, if you're going to build a new gas plant with carbon capture, you're switching on a continuous source, and that's different. And the maximum difference between the CO2 and methane over a shorter period, if you do that, per ton emitted, is a factor of 28. And this has not been taken seriously enough, and it should be charged. Governments are talking about charging for CO2, but they're not charging for methane. Now, however much wind and solar is built, they can never meet all demand. So to find the need for storage, we have to compare wind and solar supply with demand, hour by hour, or shorter resolution if we had it, over as long a period as possible. So if you look at this plot here, if we, here we go, yeah, if our mixture of wind and solar could meet 20% of demand, you wouldn't have to throw away any of it. You could use 20%. But as you go up, this curve turns over, and you have to start throwing it away because it gets bigger than demand. And the striking thing is that if you make it equal to demand, the supply, you can use 80%, you can use 80%, and you only have to meet 20% from other sources. But even if you double that, which costs you a lot of money, you've still got to meet 8% from other sources, and this never goes to 1. So people say to us, why do you want all this storage? Just build more wind. The answer is actually we fix the amount of wind to minimize the cost. And there is a minimum, as you'll see, somewhere in here. But you cannot fix it just by building more wind. Now, we use a model that we got from AFRI, the consultancy, of 2050 demand of 570 terawatt hours. And we simply repeated that 37 times in order to compare with the 37 years of wind and solar data that we used in the Royal Society report. We're using more now. Actually, as we'll see, if we talk about the amount of storage in terms of the number of days of demand it has to meet, is not very sensitive to the level of demand at all, and nor is it sensitive to the profile. The 80-20 wind-solar mix, which maximizes the amount that can be used directly and doesn't have to be thrown away, giving you headlines in the Daily Mail. Now, what I've done here is I've set supply equal demand over 37 years. So I'm going to look at the top two graphs, that's in January and July, in 1992, which is a fairly typical year. And if you had nothing but storage and it was perfect with supply equal to demand, you could meet all demand. Now you see there are times when there's too much, so you have to store it. There's times when there's too little, and you have to pull it back from storage in that hypothetical case, and so on. If you push up the supply, you go out bigger than demand, but of course there are inefficiencies, so you can't use it all. Now, when you come to the summer, demand is lower. Oh, by the way, you can see weekends in here. You notice that, these dips, those are weekends. The supply is lower. Now, the focus in most of the literature is on this, it's fixing this relatively short or medium-term variation. That's relatively easy to deal with. The real problem is long-term variability. And let me note here that the volatility is the issue. It's not seasonality. You read often, we need interseasonal storage. Actually, with this mixture, by design, sometimes there's an excess of supply is bigger than demand in the summer, and you have to store the energy and use it in the winter. And in other years, it's better in the winter. You have to store it in the winter and use it in the summer. That's how we fix the balance. So talk about interseasonality is wrong. So here again is with supply equal to demand. And this plot, you can see this partly in the thing that I put in the poster. And the real problem is that in this period we looked at, there are these 3 years of very, very low wind. These are called Dunkelflaute, periods of low wind, nice German word. And you can ask, Could you meet this with energy that's been stored here? No, it's not enough. Could you meet it with energy that's stored here? No, it's not enough. In fact, to fill this hole, you'd have to have some energy that had been in store since the very beginning, back here in 1980. That's just a fact of the wind and the weather. If you put up the efficiency, again, these deficits go down, some may turn into surpluses, but you can't use all the surpluses because of the inefficiency. Now, I'm going to begin by talking about what we called in our report our benchmark model, which we don't advocate. This just has very long-term storage, wind, solar, and some batteries to deal with very short things like a trip in the system, half-time in the cup final, all that sort of stuff. Now, they don't deliver much energy and they have really no impact on the energy from other stores. So this is a benchmark that we then use against which to measure other options. And this is the thing that I would change if I wrote it again. I would stress that even more strongly, that we don't advocate it, because we came out with a very large amount of storage. And a lot of readers of the report said, this is ridiculous, we'll never have that much storage. I don't think it's necessarily the case, actually, and they stopped reading. But if they're the next sentence that says we don't advocate this, and they've gone further into the report, you'll find that we looked at many other sources of supply and demand. So if you're good, but you're going to have something. You can't avoid storing something for 37 years in this case. If you want to store something for a very long period, you need a low cost per unit of energy stored of something which is stable. And that basically means it's storing hydrogen, possibly ammonia, I'll come back to that, in solution mined salt caverns. You couldn't conceivably store all that in batteries. And our friend Peter Edwards and Peter Dobson keep writing to the Times saying, you can't do this with batteries. Yes, that's obvious. You'll be bankrupt in no time. But you can do it with hydrogen. This is 1,000 times more than our capacity for putting, pumping water uphill and letting it down again later. So you can't do it with pumped hydro either. It's going to have to be hydrogen, ammonia, or possibly e-fuels. So I'll come back to those. That's methanol artificially made. So it's necessary to study continuous sequence of as many years as possible to identify long-term storage need. Now, there's a lot of studies that look at individual years who say, rather than a sequence, they simply cannot see this long-term need. The people who do that say, oh, it's okay, we looked at a low weather year. But you can't see that long-term need. You'll get a different mix of sources and supply, but you won't see the long-term need. This is seen in our benchmark model, which is not advocated. So this is in the benchmark model. This plot here shows in the hydrogen store, what is the amount of hydrogen in the store over 37 years? And it's jigging up and down every hour, which you can't see on the scale. But you notice that if we looked at these 30 years in the middle here, well, the size of the store is the difference between the maximum and the minimum. And then I added contingency. I'll come back to the contingency. If we... I should use that for the cursor, should I? Okay. Right. So if you look at these 30 years rather than 37 years, the difference between the maximum and the minimum is a factor of 2. Okay, so you see immediately If you look at short periods, you get the 30 years, you get it wrong by a factor of 2. If you look at individual years, you get it even worse wrong. So you must look at long periods. Another important point is that already in the benchmark model, this is a 2-variable problem. I'm often asked, how much storage do you need? There's not a unique answer. You can have a relatively small store filled very rapidly, or you can have a very large store filled very slowly within limits. You've got to have enough in the store to meet the maximum demand, so the store can't, there's a limit that way, and it's got to be big enough to meet demand. So there's a range, and in fact, there's a trade-off that depends on costs in the model between the cost of the storage and the cost of whatever you use to fill it. Electrolyzers. So this is, it's not that simple a problem. Now, here we go. I'm now going to look at the average cost of electricity in the benchmark model, but to some extent just to show you that we did a lot of work. For wind and solar, we took DESNZ. Now, for those who don't work on energy, I have to tell you what DESNZ is. That's the Department of Energy, Security and Net Zero. It used to be part of BEIS, the, whatever that was called, Business Energy or something or other. Anyway, now our ministry is DESNZ. We took their projections for cost of systems commissioned in 2040. We're really interested in 2050, but of course, what's in place in 2050, commissioned in 2050, won't be operating till later, and some of the things there in 2050 will have been commissioned earlier, so that's a sort of compromise. Since then, the projections have increased dramatically, the cost of wind and solar, and I'm going to show you that in a minute, due to increases in commodity prices and bottlenecks in supply chains. But these factors affect all forms of supply and storage, and all other forms of supply, like nuclear. For hydrogen storage, we took costs from an Equinor-led study of storing hydrogen in 10 clusters of 300,000 cubic meters solution mined salt caverns in Yorkshire, which share these clusters common facilities. Now, this is just a picture of what happens. They're very deep. They're about a mile deep, these things. So you pump down water, it dissolves, that gray stuff is the salt, dissolves the salt, and then you pump it out again. Now, some of our critics have said, hey, you can't rely on that. This is untried technology. Not true. There is vast experience of storing hydrocarbons in just such caverns. There's thousands of them all over the world. And there is also experience of storing hydrogen. In Texas, there's 3 big stores, one of 1 million cubic meters almost, that have been in operation for a very long time. And there are 3 stores, not as big, that have been in operation on T's side. So, you know, it looks as if this is safe. Each cluster stores 1.22 terawatt hours lower heating value. That's the one unit for measuring the energy in hydrogen, of usable hydrogen, which with our efficiency would give 67 terawatt hours of electricity. And Equinor thinks it would cost £247 per megawatt hour MHV. But given the lack of recent experience and the fact that we're doing things underground, you don't know what hazards you're going to meet until you do it. We rather conservatively took their value as the low value, and we took a value that was bigger and a value that was a lot bigger. Insofar as possible, and you can find this in the backup slides, which I'll make available. We also compare with studies done in the rest of the world, but it's very sensitive to a number of things, so I won't go into that. Is there enough capacity for this in Great Britain? There's much more potential capacity than needed in East Yorkshire, and there's some in Cheshire and Wessex. So yes, there is enough, but it's not all where you'd necessarily want it. There's none in Scotland, for example. Conversion of hydrogen to power. Most of the literature talks about using combined cycle gas turbines. They're more expensive, we think, than fuel cells or four-stroke engines if they were purpose-built. But although they're more expensive, we expect that initially to use some converted natural gas turbines. That's particularly true because, likely because Drax, a big coal power station that you see if you drive up the M6, is very close to the salt deposits. Now, we think that fuel cells are going to be cheaper, and reversible solid oxide fuel cells are very attractive. Now, if you think about it, an electrolyzer, which turns power into hydrogen, and a fuel cell, which turns hydrogen into power, they're the same things run in the opposite direction. So why do you need both? And the reason is that in alkaline fuel cells, you need a different catalyst going each way. So unless a very smart graduate student can find one with the same catalyst, you can't do that. But solid oxide fuel cells can run in both directions. And what's more, with a solid oxide fuel cell, if you have enough output capacity to meet demand when there's no wind and solar, you've got more than enough to store everything, which means you can have a fast-filled cavern and you can have a smaller cavern, so there's double win, if you like. Anyway, we assume 55% efficiency, low, medium, high costs of these units. But, by the way, we gave everywhere in the report the costs in the units in which they're quoted in the literature that we use, so dollars in this case. Now, I looked back yesterday at the exchange rate, and we assume that $1, the £1 is $1.35. Been up and down since then, but yesterday, guess what? It was 1.35, exactly what we assumed. And with the euro, we assumed 1.18. It's been up and down. Yesterday, it was 1.14. So these things come out in the wash, if you like. Now, costs in the benchmark model, which we do not advocate. So these are all in 2021 prices, and they include something for batteries and transmission from the wind and solar farms to the stores. And these were what for then projections for low, medium, and high cost of wind in 2040. Those all look much too low now. But the main thing is there's a huge suppressed zero here, that the cost is dominated by the cost of the wind and solar. The cost of the stuff you use, it matters, but not hugely. Also depends on the discount rate. This confuses some economists because it doesn't go in the way they expect. You have to discount to get the present value. You have to discount the energy, get the net present value of the energy that's going to be produced and divided by the net present value of what you're going to sell it for. So there's two things involved. Okay, it now expected that it's much higher the cost than when the wind was reported. These costs, by the way, are higher than in the last decade when the average coach, that should be cost, obviously. It was just unabated gas. And the average cost was £46 a megawatt hour, all in 2021 prices. But it was lower than in most of 2023, when the costs were about £300, and quite a lot lower than in 2022. Now, here's an important point. The electricity from store is very expensive. If wind and solar cost £35, which is not a value we'd use now, you can't use all of it. You have to throw away 9% or find another use for it. So the amount that goes directly to meet demand costs more than £35. But the electricity that's been through storage costs £188 per megawatt hour, partly because it must be able to meet the full demand when the wind and solar is essentially zero. In other words, there's a very low load factor in technical jargon, about 14%. Now, it's important to realize, and those average out to the numbers that you've got in the plot. This is true whatever complements wind and solar, and the alternatives look more expensive. Now there's a really big question. Will investors be willing to fund the essential but expensive long-scale storage that's going to be needed? And who's going to pay for a store in which the energy may not be used for 30 years? I'll come back to that. Okay, now here's a breakdown of the average cost. In this case, I included the cost of some batteries, rather conservatively, about £1 a megawatt hour, transmission from solar and wind farms to storage, £3. And I took the central cost projection in the Royal Society report. Now you see the cost of wind and solar, as I have more and more wind and solar, it just costs you more. Up it goes linearly, okay? But the amount of storage we saw goes down, but never to zero, so that's a brown plot. And then there's a soft minimum in the middle. It's what I said before, there is a minimum somewhere in the middle here. And you see this same thing here in Technicolor. The same thing here, again with a suppressed zero in the benchmark model. Now, I'd like to say a few words about uncertainties in the projected cost of wind. So we used in our report what BEIS, the Department of Business, Energy, Industry, and something, science, that's it, were using when we wrote the report. And then they were predicting, put into 2021 prices, that wind would cost, their central prediction for the cost of wind was £59 a megawatt hour. Then in 2023, they were predicting £36. And then it shot up to £86. So what the hell's going on? Well, it happens that, in fact, on the day our report was published, the DESNZ, as the ministry then was, published the outcomes of some bids to supply offshore wind. And they got no bids because the suppliers said the strike price, I'll say what that is in a minute, was too low to cover rising costs caused by rising inflation, supply chain issues, and higher financing costs. And rather surprisingly, DESNZ, as you can read below that, said there is significant uncertainty about how long commodity price increases, current economic pressures will persist, and therefore this is not factored into our modeling, and we continue to have confidence in our assessment. Which is a slightly strange statement, but nevertheless, by 2026, January this year, they changed their mind and they were predicting 85.9. Now, what is the strike price? This is for the non-energy experts. the government has auctions to supply, let's say, offshore wind. And the suppliers are asked to say, we will supply it for the following strike price. And that means, and then they take from all the bids, everybody has to go to the lowest strike price of those who bid. So the strike price is a fixed amount of money for a certain period, like that. And what happens is that if the actual price is bigger than the strike price, because they sell it in the market in competition with different things. This is for supplying wind, offshore wind I'm talking about. So the market is, you know, the actual price of electricity is for all forms of supply. It could be higher, it could be lower. If it's lower, then above the strike price, they have to pay the extra back to something called a government agency called the Low Carbon, what is it, the LCCC, the Low Carbon something or other company. And if it's below it, they get paid by that company. Now, what's the point of that? The point of that is that it gives them long-term certainty. And it gives us, the suppliers, we know that for that, that's what we're going to be paying for wind. Now, by the way, these strike prices, you have to be very, very careful, because originally they were always quoted in 2012 prices. Now they've suddenly started quoting them in any old prices, depending on what year it is. So I've converted everything to 2021 prices, so they're all comparable. Now, if we look at the weighted future costs of our wind and solar mix in 2021 prices, the January 2026 central projection from DESNZ would have been £61.50. They also, deep in the literature, they give some elements of the cost of low and high projections, but they never converted, although we begged them to do so, into the cost of electricity, and I didn't have the energy to do so. It's a lot of work. So I don't know what the low and high costs are. I actually guess I've written this down somewhere, I guess that they are about £52 the low and 76 the high. But we also took the bids that were in January and some last week, actually. With those, averaging Scotland and England were different. So these are actual bids put in. Whoop. Oh, hell. We get £58. So something like £60 a megawatt hour is a reasonable cost. But we'd like to look higher and lower, but probably not below 40, but maybe up to 80. And we haven't done that yet. We've only gone up to 70. Now, a few questions raised by our report. Can demand management help? After all, we're talking about supply matching demand. I've been talking about variations in demand and supply. Could we adjust demand? And the answer is, first, demand management is used in two senses. One is just being more efficient, using less energy. And that's built into models like FRS. May or may not believe it, but they've built it in. The second is shifting demand. But conventionally, shifting demand means by a few hours, to avoid the peak hour in the evening. That's not going to help you when the hydrogen still is emptying over 3 years like that. You can shift demand by 3 hours, it won't make the slightest difference. So the answer is, with conventional demand management, won't help. However, we looked at something which was new, with a term that I think I invented, which was preemptive demand management. If you go to the Met Office and ask, can you tell me what the wind's going to be like for the next 3 months? They say yes. And you say, what's it going to be like at the height of a typical wind turbine? Can you tell me that? And they say yes. So we said, supposing that in the next 3 months, let me get the numbers right here. Supposing, what slide are we on? 11. Yes, in the next 3 months, the supply is, the wind is going to be less, it's going to average 80% of the average for those months. If you could reduce demand by 2.5% by increasing prices, you could reduce the size of the store by 10%. If you said, I'd rather say, I don't want to reduce by that much. By the way, there are 26 such months in the 37 years studied out of 444 in that period. So it's not a huge amount. You could also do the same thing with reducing by 1%, but more often. Why did we choose 20% contingency? It's a guess, and it's a guess because when we talked to the Met Office, they said they had modeled at our request 10,000 winters or something like that, and they'd gone back in the historical record 100 years, and they said that they found a 10% chance per decade of a winter month with less wind than in any winter month in the 37 years we studied. So we said, okay, we'll put in 20% contingency, but it's just a guess. And the contingency will be built last, and by then we're going to need more about the weather. A much more serious question is, what about climate change? Now, the Met Office, this is in their literature, and I can see Miles laughing already. The year-to-year variability of wind is expected to continue at today's level and to have a bigger impact on electricity supply than climate change. Now, if that were true, we're okay using historical data with some contingency. But if Tim Palmer was here, he would immediately jump up and say it's probably not true. And that's not true for two reasons. The wind supply we get is dominated by two things. The North Atlantic oscillation, that's what drives the Gulf Stream. That's due to a pressure difference between the Azores and Iceland, and we all know that's changing. But more seriously is the Arctic oscillation. That's driven by a temperature difference between the Arctic and the tropics. And we know that the Arctic is warming up faster than anywhere else on the planet. So that is going to change. So there are going to be changes in the wind. So it's not obvious that using historical data is accurate, but what else can you do? I don't like to stress these uncertainties with government because they say these guys don't know what they're talking about. It's an excuse for doing nothing. What about imports through interconnectors? In the Royal Society report, we argued that they'll help manage the system, but you shouldn't build a system that fails if imports are not available, because you can have wind droughts that cover the whole of Northern Europe, so nobody's going to sell you anything. Other forms of store, we looked at a wide range qualitatively in the Royal Society report. That's on the next slide. Other sources of supply. There are some simple estimates in the report. These conclusions have now been extended and quantified. Now, what did we look at? So you need, I'm not going through this slide, you can find it all in our report. You need to classify storage by how often it has to be cycled. So a battery, for example, is very expensive. And if you don't use it very rapidly in a few hours, you will go bankrupt. It's short duration storage. Then there are things that have to be in cycle times up to a couple of weeks, some cases months, medium duration or energy storage. And then there is very long duration energy storage. Unfortunately, DESNZ and its advisors refer to this middle category as long duration energy storage. And they don't know anything about, they don't mention the long duration energy storage. So it's very dangerous. According to Wittgenstein, philosophy is a battle against bewitchment of our intelligence by means of, I should say, language. And that's happening in this case. We really need to get people to talk about medium development energy storage, and because they've taken away long-term storage, we've used very long storage. And we looked in most detail at something in all three categories. Lithium-ion batteries, ACAS is an exemplar of the second category, and hydrogen and that cost. Now, what is ACAS? That's adiabatic compressed air storage, or advanced compressed air storage. Now, the problem with compressing air is the idea is you compress air, you store it, and then you let it out again, it drives a turbine. Now, as you know, when you've got a bicycle, when you compress air, it gets hot. When you get out again, it gets cold. So it freezes the system. So there have been two systems of compressed air been in operation since, one in Germany has been in operation since 1978 and one in the US since 1991, which, to stop it freezing, burn natural gas. It's hardly in the spirit of net zero. So a better idea is to store the energy of compression and put it back again when you expand. So that's the advanced compressed air energy storage. Some people have said to us, but that's never been done. You're out on a limb here. Not true. When we wrote the report, there were already 3 compressed air storages, this was a year and a half ago, delivering energy to the grid in China. And this morning, I asked an AI program, how many are there today? And it said that's classified information. But I can tell you there's at least 4, probably 5 or more, and they've made it a priority. So the Chinese has, according to the program I used, at least 2 gigawatts connected to the grid of compressed air storage. We could have also looked at liquid air storage, and there is a system being built in the UK which is going to come online near Manchester later this year or next year. But we didn't, I think, because the modeling was done by Seamus Garvey, who's very interested in compressed air, although the person who drove the liquid air is Llewellyn Ding from Birmingham, was part of our group. Now, beyond the benchmark model, oh God, I'm going to run out of time. Ammonia could do the whole job and be located anywhere. If you said you used only ammonia with no hydrogen, the average cost of electricity will be about £5 per megawatt hour greater. But nobody's talking about using all of it. And these are tanks being built in Qatar, actually. 100 such tanks will provide 1/4 of GB's long-term needs if you took a mixture, and 1/4 is probably more than you need. So we can imagine having a lot of hydrogen tanks, and then in parts of the country like Scotland, where there's no salt, some ammonia. Hydrogen and ACAS could lower the cost. It depends on the cost of ACAS is badly known, perhaps by 5%, and reduce the need for hydrogen storage. But they would not remove it. You've got to have some long-term storage. Nuclear baseload, and I'll explain this, increases the average cost of electricity unless the nuclear cost per megawatt hour is less than the average cost of power without it. Flexibly operated gas plus CCS could lower the cost, because we don't know, but new work makes this look very unlikely. It could remove the need for large-scale, it could not remove the need for large-scale storage. And note, we should be putting in the costs some methane cost. Imports, as I've said already, can help manage the system, but they don't remove the need for storage. Now, quickly, beyond the Royal Society's support, there's a paper in preparation by Ian Garvey, Seamus Garvey, myself, and Ian Staffel. It looks at 45 years of data rather than 37. That's thanks to Ninja Renewables, which take the actual weather and turn it into wind and solar output, of which Staffel is one of the authors. We explicitly include demand correlation with weather. Ian took the AFRI demand. AFRI based their demand model in the weather in 2018, and then we repeated it 37 times. Ian has a magic way of taking out the effect of the weather and then putting it back again for all the years. We've looked at how valid it was to regard interconnectors only as possible additional contingency rather than essential sources of flexibility. We've looked in more detail at the input of gas-fired generation. And much more, the key thing is different combinations of flexibility mechanisms using much more sophisticated modeling. These pictures mean nothing. I don't know why Seamus put them in there. Now, using 45 years, these are the conclusions, is better than 37 years. If you can go to an infinite number of years, the error goes to zero. But it doesn't change the system that minimizes the cost very much. Analysis based on repeating pattern of just 1 year simply get the wrong answer, quite seriously wrong. The drivers for flexibility are predominantly on the supply side. What you assume about the profile makes very little difference. We confirm that interconnectors won't help us much. In a net zero system, sourcing more than 2% of electricity, if you force it to use electricity, will push up costs and have profound impacts on the optimal use of hydrogen storage in the system. We actually think that if you took, which we haven't done yet, more realistic costs for gas, and we put in a carbon price and or CCS, there's probably, on economic grounds, you wouldn't use any gas. Nuclear power would have to come at a relatively low cost to reduce the system's cost overall. Now, very quickly, this is I'll really just show a couple of slides, I think, and I'm running out of time. When you model, if you've got one type of store, it's easy. You ask yourself in the next hour, is there going to be a surplus of wind and solar? Put it in the store. That's in the benchmark model. Is there going to be a deficit? Take the energy out of the store. But with multiple types of stores, if an excess is anticipated, you need to decide where to store it. Are you going to put it in hydrogen, in batteries, in compressed air, whatever? And you have to decide what source to draw on when there's a deficit. In other words, you have to have what in the trade is called a merit order. Now, our method, based on a proposal by Stan Zachary, implemented by Seamus, is publicly available on a website which includes a video in which Seamus explains how it works. The essence is, don't use hydrogen when the store is nearly empty, as if it becomes empty, the lights will go out. So that's really dangerous. And use it if it's almost full, if there are other things available, and in between decide on the grounds of efficiency. So technically, we attack a marginal cost to the value of the energy in the store, which is big if it's nearly empty and low if it's nearly full, and something in between, and then we have a merit order based on that. And this is the other thing that's new. In our report, we made some guesses about the use of gas, so the back of the envelope, a bit more than that actually, but we didn't model it systematically. We now realize that you can treat gas as a store that you don't have to replenish. North Sea is always there. So you just, and then at the end you asked, how much has the gas have you used over 37 years or 45 years? And you add the cost of that to the cost. So we're now able to model mixtures of many different sources and stores. By the way, we've been using this in MATLAB on a laptop. And to study 45 years of weather with 4 different types of stores and sources takes 60 hours. The level of wind and solar is treated as a parameter, so it's to be fixed in the cost minimization. This time is recently reduced by rewriting the whole thing on Python, and it's still only 8 hours. It's still 8 hours, still on a laptop. So this doesn't take colossal amounts of time. So that's what we did. What did others do? So we don't know, actually. We talked to the people in Desnes, and they have paid a lot of money for models, but they don't really seem to know how they work. And but they assume, most of these models, some of them anyway, we know, assume perfect foresight to match the use of stores and other sources in a way that minimizes costs. Now that's obviously wrong. We don't have perfect foresight. What's more, it makes it impossible to study a long period, because if you're going to use perfect foresight, you have to look at every hour in the period at once, and there are 330,000 hours, and you'd have just amount of computing power sort of more than in the universe. And it's wrong. As to see the need for long-term storage, requires looking at very long periods. We think they also modeled using a merit order based on costs, but this is hard to, at least they once said something like that to us, very hard to understand, as the costs depend on load factors, but you don't know the load factors before you model. So that makes no sense. So we don't know what they did, but we know that, well, we think they ought to be using some variety of what we're using. Now, I see I'm running out of time, so I'm going to skip all this and come to the conclusions. Actually, before that, let me say that I've put the slides I've skipped, they're all in the backup slides, and there's a lot of issues covered in the Royal Society report and the supplementary information that I didn't cover. The possible use of depleted gas fields or aquifers to store hydrogen, whether it's best to put the electrolyzers close to the source and transmit hydrogen, or transmit electricity and put the electrolyzer next to the store, whether there's enough water for the electrolysis, and so on and so forth. Now, here's the conclusions. There is a need for large-scale, long-duration storage in North Europe, driven by the North Atlantic and Atlantic oscillations. Northern Europe is not an outlier. We looked at the Dogger Bank, and there you see the annual and cumulative surpluses. And we looked at Vineyard, that's a place they're building off Martha's Vineyard, and it's very similar, although displaced, they're out of phase. But then we also looked at Texas, and it's just the same, really. So you must assume it's necessary to study long periods in all regions until modeling shows otherwise. You can't just assume I can get away. It could be there are places in the world you can get away with modeling for fewer years, but you don't know that unless you've tried the longer years first. You need at least 15 days of demand, and that depends very much on the cost of the medium duration storage. if you express it in that way, it doesn't depend on the level of demand. If you express it only weekly in the number of days of demand you have to meet, and it's very weakly on its temporal profile. We assumed a flat profile just to see what would happen, and to get the same answer, more or less. This is best provided by storing hydrogen in solution-lined caverns, possibly some ammonia. With the best possible projections, it appears that net zero can in principle be reached in 2050 with an average cost of electricity higher than the last decade, but comparable to the cost in the last few years. I'm not certain of that because we haven't redone all the costing. Now, my final slide. Further steps. There's a need to look at the need for and the cost of hydrogen for electricity storage together with other potential uses of hydrogen, because there are probably systems benefits in using both. If there aren't, you wouldn't do it. If there are, it'll bring the cost down. We don't know what they are because we don't know what the uses of green hydrogen are. And the people who study green hydrogen tend not to tell you how flexible it is, so it's not possible to study it. NSTOR SIM is publicly available. Anyone who wishes can use it to study Great Britain's energy system using their own assumptions about sources, stores, and costs. And we hope that DESNES and NESO, the National, Energy, what does it stand for, Nick? You must know. National Energy Systems Operator, and those who advise them will do so. We've provided a methodology that allows them to study long periods with a mix, and we think with that, our job is done. And their job is to go back with much bigger teams on our back of the envelope efforts and look at all the costs and redo it. Now, I've got to say one other thing before the policy implications. Well, we're in a physics department. What about R&D? There's huge scope for improvements in most systems under consideration and combining them in new ways. Seamus will kill me if I don't mention wind integrated storage. That's a system where on an offshore wind farm, you would use the mechanical power of the turbine directly to pump water up into a tank rather than turning it into electricity. There are other things that can be done. Reversible electrolyzers, fuel cells, reversible compressors and expanders, reducing or eliminating iridium in PEM electrolyzers. As far as we could tell, that's the only resource constraint on what we've done. And if you ask, if you did everything we wanted, if you wanted to do it with electrolyzers, you'd have trouble with the amount of iridium. And finally, another one will be, and Edmund Sang in Oxford is working on this. We know in the lab how to directly electrochemically synthesize ammonia from water and air, but it's very inefficient. And after that, we need demonstrators. Last point. The UK government is focused on clean power in 2030. It should be cleaner power because it's not clean. They haven't given enough thought to what follows. You need to have an idea of where you're going in order to start off in the right direction. They stressed gas and CCS and new nuclear, neither of which will be available by 2030 and could land us with stranded assets. It's really important to seek to minimize the emissions with the lowest cost pathway to 2050 in demand. The components of the hydrogen and ammonia storage are ready to be deployed, and that's true for many of the medium duration energy storage, and there's a case for large-scale demonstrators. The construction of wind and solar capacity and work on strengthening the grid should be accelerated. The construction of the large-scale electricity storage should begin now, so that what is going to be needed will be available when it's needed. And there's an urgent need to develop and implement market mechanisms, and sorry I had to skip the slide on that, that will attract private investment. Thank you very much. I'm sorry I went over.
Thank you, Chris, for presenting those important results on something, and doubtless there'll be more work on this in the future. Now, some people may have to go, so if you want to slip out quietly, but meanwhile, perhaps we can have, we are late, quite a bit late. Perhaps we can have one or two questions before we go on this important issue. Miles. I'm sure you have a question. Paolo first.
Yes, so thank you very much, Chris, very, very inspiring. So one question I have is, you told us various prices and various scenarios, and you also mentioned other options. For example, what I would consider the standard model, which is essentially solar wind plus nuclear plus a little bit of energy. But you didn't tell how much that option, which has very low risk, you don't store in hardly any energy, how much more would it cost, and then how much consideration going into that part?
Oh, since you've asked.
Yeah, I saw the slides. I want to see the slides.
Oh, hell, I'm not going backwards. Oh, I got to the end. How did I do that? Oh, I see. I'm pressing the wrong direction, wasting time. Okay. So nuclear provides base load, sounds very reassuring, but it's almost a theorem that it costs more per megawatt hour than a combination of renewable energy and storage. We recognize there could be a possible role based on the speed of deployment, but also cost if small modular reactors live up to what their proponents think. And they provide inertia. Also, they provide diversity. We don't know how to value that. But I notice our system, in a sense, it's got the resilience that comes from diversity. I mean, we've got lots of small systems. They're not all going to crash at once. Now, here are the numbers. Oh, hell, that's the wrong way again. If you added nuclear, you will want to run it flat out, okay? So it removes the bottom half of demand. So it makes the remaining bit more variable. So meeting that with wind and solar becomes more expensive. That's sort of almost a theorem. Now, what we found is that in the reference case, depending on the cost of the wind and solar, the cost of power was 71.8 pounds a megawatt hour, 50 pounds per megawatt hour. Let's look at that. With demand reduced by 5 gigawatts, the bit that goes up, and that's because, as I said, it's more expensive. To maximize the cost with 6.5 gigawatts of nuclear power, a way that averages the average cost, it would have to cost less than 68 pounds. Now, is nuclear, and with 70 pounds, it's a different number. I hope these numbers are right. I found a mistake in them yesterday. Now, what should you compare them? Hinkley price, point, 170 pounds, 7 pounds per megawatt hour, all in 2021 prices. Sizewell C is going to be funded on what's called a regulated asset basis. That means the providers agree with the government what it actually costs, and they pay them that. Now, the government thinks the cost of power on a regulated asset basis from Sizewell C could be 51 to 59 pounds, which would lower the cost. But the Financial Times wrote last year, financing and interest costs could push the economic construction cost to 65 to 60 billion or more. So the fact is we don't know. I'm probably the only person in the room old enough to remember in the 1950s, we were told nuclear will be too cheap to meter. It never happens. The costs are always high. Modular reactors could be lower. Rolls-Royce is pushing them very strongly. They talk about small modular reactors, but they're not actually very small, the ones they're advocating. But the idea is to build a lot that are identical, maybe in the same place, with the same people in the factory. But this won't be known, not a mistake, until several have been built, and none will be delivering power before the early to mid-2030s. So there could be a role for nuclear, yes.
Well, the answer was yes, I think. Listen, I think it is quite late. So what I suggest is that we call it a day today. And if anybody has further questions, perhaps they can come down to the front and ask Chris. Let's thank Chris for the colloquium today.